Okay, in the previous class, we have discussed FFT algorithm using the divide and rule approach. So, okay, so what we have done there is that when you compute the endpoint DFT of a sequence, so we have decomposed n into two factors, L and M. Okay, and then we have stored this data, that is n samples, in a two-dimensional matrix of order L cross M. Okay, and we have stored the data in column wise format. Okay, it means you fill the first column, then you fill this next column, and so on. And then what was the algorithm? The algorithm was first to compute the m point DFT of each row, first step. Okay, the second step was to multiply each element of the resultant matrix with a phase factor, and then finally you have to compute the L point DFT of each column. This is the methodology that we have used in divide and rule approach, and using this we have seen that we have reduced the computational complexity as compared to the direct computation of DFT. Okay, and then we have uh, discussed that when n can be expressed in the powers of 2 only, n is equal to 2 raised to power r, that means it can be 2, it can be 4, it can be 8 or 16 or 32, 64 and so on. If n can be expressed in the powers of 2 only, in that case you can develop a more, you can say, computationally efficient algorithm which is called as Radix 2 FFT algorithm. Okay, and you will soon see that in this case what is basically left is, suppose you have to compute 16 point DFT, so you first divide 16 as 2 into 8, then this 8 is further decomposed as 2 into 4, then this 4 is further decomposed as 2 into 2. Okay, so what you finally get is only 2 point DFTs, so you get a symmetric structure. So by combining the 2 point DFTs you generate a 4 point DFT, then by combining to 4 point DFTs you generate 8 point, and then by combining to 8 point you generate a 16 point DFT. Okay, and even if the length of the sequence is not is equal to 2 raised to power r, you can pad zeros and you can make this length equal to 2 raised to power r. Like suppose if you want to find n is equal to 15 point DFT of a sequence. Okay, so what you can simply do is that you can pad 1 zeros to this sequence so that the length becomes 16, and then you can use Radix 2 FFT algorithm. Okay, so in the Radix 2 again there are two algorithms. One is called as decimation in time, one is decimation in frequency. Which we call as DIT FFT. Okay, we will discuss this algorithm first. So we will discuss decimation in time, DIT, Radix 2 FFT. Okay, so what we do in this case, we decompose again n in the form of two factors L and M, and we choose L as 2 and M as n by 2. Okay, so it means you store this data in a matrix with 2 rows and n by 2 columns, like this. So this is a matrix of 2 cross n by 2 order. And if you again store the data in the column wise, so you'll get x0 here, then x1, then x2, x3, x4, x5, 6, 7, so on. Okay. Now using this decomposition, what you will see that in the first row you get the even samples, even numbered samples. Okay, I can write this as x of 2n, this sequence. And in the second row you get the odd samples, x1, x3, x5, x7. So I can write it as x of 2n plus 1. Okay, so using this decomposition, 2 into n by 2, we are basically dividing this input sequence into 2 sequences. The length of each sequence is half of the original sequence. So one sequence contains your even sample, the second sequence contains your odd samples. Okay. Now this endpoint DFT xk, which was summation of xn wn to the power kn, n from 0 to n minus 1, you can write it as x of n wn to the power kn for n even samples, and one summation you can write for odd samples. Okay. So in place of using the 2 summations, we have used one series for even. We have separated basically the even and the odd sequences. Okay. Now when n is even, it means your n is 2n. I can write it as x of 2n wn to the power 2kn, and n in this case will now go from 0 to n by 2 minus 1 only, because first n by 2 samples, half samples. Okay. Similarly, in the next case, when n is odd, it means you have x of 2n plus 1 samples here, and wn to the power k, n will be again 2n plus 1. Okay, so n from 0 to n by 2 minus 1. Okay, so this sequence will give you the even points, this will give you the odd points. See, when n is equal to 0, you'll get x0. If you expand this equation, it is very simple. You may not be able to understand. Let me elaborate it. My sequence was xn wn to the power kn, n from 0 to n minus 1. So if I expand it, it becomes x of 0 wn to the power 0, it is 1, then plus x of 1 wn to the power k, then plus x2 wn to the power 2k, plus x3 wn to the power 3k, and so on. So what I have done simply is I have combined the even samples in one series and the odd samples x1, x3, x5 and other samples. Okay, so if I expand this equation, I will get the even sampled. It means when n is 0, you will get x0 here. If you expand this series, if you expand it, what you will get? When n is 0, you will get x0, plus when n is 1, you will get x2 wn to the power 2k, because n is 1. When n is 2, you will get x4 wn to the power 4k, and so on. Similarly, if you expand this equation, you are getting the odd samples. When n is 0, you will get x1 here, x1 wn to the power k. Similarly, when n is 1 here, you will get x3 wn to the power 3k and so on. Okay, so I have simply divided into odd and even functions. Okay, so this sequence I can further write it as xk is equal to summation of n from 0 to n by 2 minus 1 x of 2n wn to the power 2kn. I can write it as wn by 2 to the power kn. Okay, this 2 I have taken here. This we have discussed in the last class how we can do it. Okay, and then we have n is equal to 0 to n by 2 minus 1 x 2n plus 1. Now in this factor you will get two terms. If you expand it, it will become wn to the power k into wn to the power 2kn. Now since this summation is with respect to n in this equation, I can take wn to the power k outside this. I can take wn to the power k outside the summation, and inside you will get wn to the power 2kn, or I can write it as wn to the power wn by 2 to the power kn. Okay, so if you further analyze it, so you have finally xk summation of n from 0 to n by 2 minus 1 x2n wn by 2 to the power kn plus summation of plus wn to the power k into n from 0 to n by 2 minus 1 x2n plus 1 wn by 2 to the power kn. Okay, so if you look to this equation, this is nothing but the n by 2 point DFT of x2n, and similarly this equation is n by 2 point DFT of x2n plus 1. Okay, so if I write this suppose as maybe f1k, so it will become f1k plus wn to the power k into f2k. Okay, where f1k is nothing but the n by 2 point DFT of x2n, that is even sequence, and similarly f2k is n by 2 point DFT of x2n plus 1. Okay, this is what is my xk. So this equation what it gives you, it gives you a mechanism to compute n point DFT by combining to n by 2 point DFTs. Okay, so if you know the n by 2 point DFT of even sequence, and if you know the n by 2 point DFT of odd sequence, you can combine them using this equation to get n point DFT. Okay, and we also use one more property here, because in the DFT of signal is periodic with n, and since this is n by 2 point DFT f1k and f2k, they are also periodic with the period of n by 2. It means in this equation, if I write x of k plus n by 2, that will be equal to f1 of k plus n by 2, which is equal to f1 of k. Okay, because it is periodic with n by 2. If I write x of k plus n, that will be equal to x of k, because xk is n point DFT, it is periodic with n samples. Since f1k and f2k, these are n by 2 point DFTs, so f1k plus n by 2 is equal to f1k, and similarly your f2 of k plus n by 2 will be f2k plus wn to the power k plus n by 2. So wn to the power k plus n by 2. Okay, what it will be? It will be e raised to power minus j 2 pi by n, which is wn to the power k plus n by 2. Okay, so you'll get two terms. One is e raised to power minus j 2 pi k by n multiplied with e raised to power minus j 2 pi by n into n by 2. So 2 and n will get cancelled. E raised to power minus j pi, it will become minus 1. So it will become minus wn to the power k, because this factor is wn to the power k, and e raised to power minus j pi from the second term you will get minus 1. So in place of this plus, you will get here minus sign. So minus wn to the power k into f2 of, it is again k plus n by 2, but that is again equal to f2 of k. Okay, so this is for k is equal to 0 to 1 up to n by 2 minus 1. The first 4 samples you will get from this equation, first n by 2 samples, and the next n by 2 samples of output you will get from this equation. Okay, so these two equations are now fundamental equations which are used to combine the n by 2 point DFTs to get n by n point DFT, and see how it is combined. So you have one equation x of k plus, sorry, one equation is your xk is equal to f1k plus wn to the power k into f2k, k from 0 to n by 2 minus 1, and the second equation is x of k plus n by 2 is equal to f1k minus wn to the power k into f2k, k is 0 to n by 2 minus 1. Okay, so if you know the 2 n by 2 point DFTs, that is f1k and f2k, you can get n point DFT from these equations. Okay, so it means if you have 8 point DFT, if you want to compute 8 point DFT of any sequence, so what we have done is that we have decomposed n as 2 into 4. So we have separated the even and odd samples. Okay, so x0, x2, 4 and 6. This is one sequence which is x2n, and the DFT of this is f1k. Second sequence was odd samples x1, 3, 5 and 7, which is x2n plus 1, and the DFT of this is x2k, suppose. So if you know f1k and f2k, you can combine them to get xk, which is the 8 point DFT of this sequence. So how we do that? So suppose I have f1k, that is this is f1k, the 4 point DFT. I am taking example, otherwise it is n by 2 point DFT of even samples. It means input for this is x0, 2, 4 and 6. And the second DFT that we have, which is again n by 2 point DFT, which is f2k, this gives me the DFT of odd sequence, that is x1, x3, x5 and x7. So suppose I know the 4 point DFT of the even and the odd sequences. So how can I combine them to get 8 point DFT? From this equation and from this equation you will get. Okay, when you find xk, x0, the first sample of output, that will be f10 plus wn, n in this case is 8, w8 to the power 0 into f2 of 0. Then you get x1. When k is 0, you'll get x1 from this equation, second. Okay, sorry, you will get x1 from this equation. First 4 samples you will get from this equation, next 4 samples will get from this equation. So x1 will be of 1 plus wa to the power 1 into f2 of 1 and so on. x0, 1, 2 and 3, when you get k is equal to 0, you will get x4 from this equation. So that will be of 1 of 0. When k is 0, it will become x of k plus n by 2, and by n by 2 in this case is 4. So it is 0 minus wa to the power 0 into f2 of 0. Similarly, x5 will be f1 of 1 minus wa to the power 1 into f2 of 1 and so on. So I get x0. This is f1 of k, 4-point DFT. It means this point is f1 of 0. This sample is f1 of 1. This is f1 of 2, f1 of 3. Okay. Similarly, this is my f2 of 0, f2 of 1, 2 and f2 of 3. So f1 of 0 plus w to the power 0 into f2 of 0, that is x0. So f2 0 is this. You have to multiply this with the phase factor, that is w to the power 0. Of course it is 1 in this case, and then you have to add this with f1 of 0. This you will get x0. Similarly, x1 of 1 of 1, this is f1 of 1 plus w to the power 1 into f2 of 1. So f2 of 1 multiplied with, if I multiply this with w to the power 1, and then I add this with f1 of 1, I will get x of 1. Similarly, x2, you have to multiply this with w to the power 2 and add with this, you will get x of 2. Finally, you have to multiply this with w to the power 3 and add with this, you will get x of 3. To get x4, you can use this equation. So f2 of 0 is multiplied with w to the power 0 into minus 1. So this branch, if I multiply this branch with minus 1, it will become f2 0 into w to the power 0 into minus 1, and then you have to again add with f1 of 0, you will get x4. Similarly, you multiply this branch with minus 1, add with this, you will get x5. Multiply this with minus 1, add here, you will get x6. So finally multiply this with minus 1 and add with this branch, you will get x of 7. Okay. So this is the structure how you can compute 8-point DFT from 2 4-point DFTs. Okay. So in general, it is to compute a n-point DFT from 2 n by 2-point DFTs. Okay. Now see, so if we have a 4-point DFT, you can combine them to get 8-point DFT. And then we have to see that how you can get these two 4-point DFTs. Okay. So to get this 4-point DFTs, you can further decompose this 4 as 2 into 2. It means this 4-point DFT can be computed from now to 2-point DFTs. Okay. So you again apply the same principle, again same mathematical theory, and you will see that now this sequence, input sequence, for this you have to compute 4-point DFT. Okay. So I can divide this into two 2-point DFTs. So if I use two 2-point DFTs, those 2-point DFTs can be combined and to get a 4-point DFT. This one. Now what should be input to this? Now input to this, now this is the 4-point sequence. It will be again divided into even and odd samples. It means in the one point you will get x0 and x4. In the one other case you will get x2 and x6. Okay. So the input to this will be x0, x4. The input to this will be x2 and x6. Similarly, this 4-point DFT F2K, this can be computed again from 2-point DFTs. Okay. Now F2K is the 4-point DFT of this sequence. Now if I again divide this into even and odd samples, so x1 and x5, that will be the input to one block, and x3 and x7, that will be input to another block. Okay. So if you know the 2-point DFT of this, 2-point DFT of this, these are two 2-point DFTs. So you can combine these 2-point DFTs to get a 4-point DFT. And how you can do that? You can use the same equation, the general equation for n-point DFT to get combine. Okay. So it means by combining of these 2-point DFTs, I can get directly this 4-point DFT. Okay. And how will combine? It's the same structure. You have to multiply this with this branch with. Now in this case, n is 4. So I have to multiply w4 to the power 0, and the second branch will be multiply w4 to the power 1. So multiply this with 0, add with this branch, you will get 1. Multiply this with w4 to the power 0, add with this, you will get the second output. Then multiply both with -1, the lower branches, and add with the top branches, you will get the next two samples. This is how you can. Now this sequence will be deleted. You will directly get here, and similarly here. Okay. I will make a different graph for this. So to get 8-point DFT, what we are doing is you are first finding the 2-point DFT. Okay. And the input to this is not x0, x1, it is x0, 4, 2, and 6. Similarly, we have another 2-point DFTs. The input for this is x1 and x5, then x3 and x7. Okay, so you compute its 2-point DFT. How you compute 2-point DFT, that is a different concern. We will come to that. But you have to combine these 2-point DFTs to get a 4-point DFT. Okay, and we have equation for this. Xk is equal to f1k plus double under the power k into f2k, and the second is xk plus n by 2 is f1k minus double under the power k into f2k. So these are general equations for any n by 2-point DFT, which are combined to get a n by 2-point n-point DFT. Okay. So if you 2-point DFTs are given to you, you have to combine them to get a 4-point DFT. So the lower branch is multiplied with w4 to the power 0 and w4 to the power 1. And since mainly we use the same phase factor, what we do, in order to maintain the symmetry, w4 to the power 0, I can write it as w8 to the power 0 because both are equal to 1. And w4 to the power 1, I can write it as w8 by 2. Okay, and w8 by 2 can be written as w8 to the power 2. So in place of w4 to the power 1, we generally write here w8 to the power 2, and this is w4 to the power 8 to the power 0. Okay, so these are two 2-point DFTs. I multiplied the lower branches with w8 to the power 0, w8 to the power 2, we add with this and add with this, you get the 2 points of DFT from this equation first. The second 2 points you'll get from this, so you have to multiply this with -1, add with this and add with this, you will get the 4-point DFT. Okay, this is how you combine two 2-point DFTs to get a 4-point DFT. And similarly in the lower side, multiply with W at the power 0, W at the power 2, add with this, you'll get 2 points, then multiply with minus 1, add this with this, and add this with this, you'll get the next 2 points. So this is now one 4-point DFT. This is another 4-point DFT. Now you have to combine these 4-point DFTs, these two 4-point DFTs, to get a 8-point DFT. Okay, so that we have seen how we can do. So for that, the lower branch will be multiplied with W at the power 0, W at the power 1, W at the power 2, W at the power 3. Okay, so if I add them directly with the corresponding upper branches, this will get x0, x1, x2 and x3, and then you have to multiply with minus 1 each branch, add with the top branch, you will get the next 4 samples, that is x4, x5, x6 and x7. Okay, so this is how you get the 8-point DFT. Now the final question is that how to get this 2-point DFT. Okay, because if you have this 2-point DFT, you can combine the two 2-point DFTs to get 4 points, then you can combine the 4-point DFTs to get 8-point DFT. Okay, and to get this 2-point DFT, it is very simple. You will see it with the same structure, because if you find the 2-point DFT of a sequence, this is n by 2, n0 to n minus 1. This is n-point DFT. If it is 2-point DFT, it means your n will go from 0 to 1 only, because capital N is 2, and you have x of n, Wn, capital N is 2 to the power kn. So first sample you will get x0, you have 2 points only. What will be x0? When k is 0, it is simply x0 plus x1, and when k is 1, it is x0 plus W2 to the power 1 into x of 1, and W2 to the power 1, if you look to this, what is it? W2, it is e raised to power minus j 2 pi by n, and in this case is 2, so it is e raised to power minus j by j pi, which is nothing but minus 1. It means it is simply nothing but x0 minus x1. This is how you get the 2-point DFT. You add the two samples, you get the first sample, you subtract the two samples, you get the next samples in the DFT. Okay, it means if you find this 2-point DFT, what I have to simply do, I have to add this with this, then multiply this with minus 1 and add with this with this. This is how you get the 2-point DFT, isn't it? If you have 2 points A and B, you want to find the 2-point DFT, they are simply added. In one case, it will be A plus B, then multiply with minus 1 and add with this, you will get A minus B. Okay, now in order to maintain this structure, this symmetry, what we do, you multiply this one branch with W8 to the power 0, because W8 to the power 0 is 1 in any way. Okay, and then add with this, then multiply with minus 1, add with this, it will be simply upper will be x0 plus x4, the lower part will be x0 minus x4, which is 2-point DFT. And similarly here, so multiply this with W at the power 0, add with this, multiply with minus 1, add with this will get 2-point DFT. Similarly here, W at the power 0, add with this, multiply with minus 1 and add here. So W at the power 0, add with this, minus 1, add with this, you will get this. This is how we get the 2-point DFT. Okay, So you first find 2-point DFTs. Then by combining the two 2-point DFTs, you get a 4-point DFT. And then by combining the 4-point DFTs, you get a 8-point DFT. Okay. So by combining 8-point DFTs, you can get 16-point DFT and so on. Okay. So this is the structure, and you will see that in this structure, there is a single structure which is repeatedly used. So you have two inputs A and B. We multiply this with W into the power R. We add with the top branch. You will get A plus W into the power into B. Then you multiply this lower branch with -1, and we again add this with this. You get A minus W into the power R into B. So this structure, 2-point DFT basically, it is repeatedly used again and again in this entire structure. This is called as butterfly diagram. Okay. So next we will see how you can find out the computational complexity of this algorithm. Okay. And how it is more efficient as compared to the direct computation of DFT.